We have looked at the position vector of center of mass. In this video we are going to look at the motion of the center of mass, meaning that we are going to find out physical quantities associated with motion like velocity, acceleration and momentum of the center of mass. Let's begin again with the position vector for the center of mass. RCM is 1 upon m sigma MIRI, and that can be written as 1 upon m m1r1 plus m2r2 and mnrn. Right? Now I want to find out the velocity of the center of mass. Right? Velocity of the center of mass would be the first differential of the position vector. So it is drcm by dt. So I will differentiate this particular term with reference to time. So I'll get 1 upon m into m1 dr1 by dt plus m2 dr2 by dt plus mn drn by dt. Right. I hope you have understood this, that we are differentiating this entire term. Masses are constant, so basically I have to differentiate r1 with reference to time. So I'm getting dr1 by dt and dr2 by dt and so on and so forth. This can be written as 1 upon m into m1. Now dr1 by dt is the velocity of particle number 1. Right? This is the first differential of position vector r1, velocity of particle 1. So this will become v1 plus m2 v2 plus mn vn. Right? This is vcm, which I can write down as vcm is equal to 1 upon m, right, sigma of mi vi, I is equal to 1 to n. So this is equation number 1, which gives me the velocity of the center of mass. Now if I differentiate this equation, velocity, again I'll get acceleration, because acceleration acm is equal to the first differential of velocity vcm upon dt. So I'll differentiate this entire term, and again what I'll get is 1 upon m and m1 are constants. So I'll get m1 dv1 by dt plus m2 dv2 by dt plus mn dvn by dt. Right. And we know that dv1 by dt, this is the acceleration of particle number 1, this is acceleration of particle 2 and acceleration of particle n. So acm now can be represented as is equal to 1 upon mass, this is the total mass of the system, m1 a1 plus m2 a2 plus mn an. Right? And this can be written as acm is equal to 1 upon m sigma m I ai raised to n, I is equal to 1 to n. So this is equation number 2. This gives me the value of acceleration of mass 1. Right? Now this equation can be written as m multiplied by acm. M I'm taking over here, right? M I'm taking over here. So m into acm is equal to m1 a1 plus m2 a2 plus mn an. Right? Now what is m1 a1? Mass into acceleration is force. So this is the force acting on particle 1. This is the external force acting on particle 1. This is external force acting on particle 2, and this will be Fn. And this will be the total external force acting on the entire system. And therefore I get the equation, let me write over here, therefore F external is equal to mass acm. Right. This is, say, for example, equation 3. And what do I conclude from this equation? From this equation you can see over the external force is acting on the entire system, and the center of mass is accelerating. So from this I can say that the center of mass of the system of particles moves as if the entire mass of the system were concentrated at it and all the external forces were applied at it. So this equation gives us that the center of mass acts as if all the external force, all these forces are acting at the center of mass, and the entire mass of the system was concentrated at it and the external forces were applied at it. So this equation gives us that. Now supposing the system is isolated, that means F external is 0. So this is for an isolated system. Isolated system. The system is isolated, that means there are no external forces. External is equal to 0. So m ACM is equal to 0. Mass cannot be 0, so ACM is equal to 0. Right? So ACM is equal to 0, therefore we can write down VCM is equal to constant. What does this mean? This means that if the vector sum of the external forces, this is the vector sum of the external forces, if the vector sum of the external forces is equal to 0, right, that means there is no external forces acting on the system, then the system is isolated, and then the velocity of the center of mass, remains constant. Acceleration of the center of mass is 0 and velocity is constant. This is a very important property of center of mass. Using the same logic again, we can find out the equation for the momentum, and momentum will come out to be m is equal to m and VCM. Right? The momentum of the center of mass would be total mass of the system into into the velocity of the center of mass. Right? The total linear momentum of the system. This is the total linear momentum of the system of particles is equal to the product of total mass of the system and the velocity of center of mass. So it is equation 4. Right? And again, we know that force is the rate of change of momentum. So I can write over here dP by dt is equal to F external. Right? dP by dt is external. Total linear momentum, rate of change of momentum is F external. Right? Let us call this equation 5. Right? And from what we conclude from this is that the change of momentum of system of particles is equal to the vector sum of all the external forces. Right? This is the sum of all vector external forces. And again, for an isolated system, right, F external is equal to 0. So again, I'll write down over here, or let me write over here, for an isolated system, F external is equal to 0. Right? That means dP by dt is equal to 0. That means P is equal to constant. Right? The rate of change of momentum, the change in momentum is 0. That means momentum is constant. So P is equal to constant, and therefore I can write down P1 plus P2 plus Pn is equal to constant. This is the sum. All of them is constant. And what I conclude from this is that when the vector sum of all the external forces is equal to acting on a system is 0, the total linear momentum of the system, remains constant. Right? So we have in some ways proved the law of conservation of momentum, which says that when external forces or the sum of the external forces is equal to 0, then the momentum remains constant. Thank you.